Okay, so yesterday we began talking about exponential growth and decay equations. Please have your notes out for that or pick up an extra out of the colored folders. I'm going to go ahead and do the example for checkpoint 1, and then you can follow along after I have the work down for that. All right, so in part A, we set up the equation to be 906, these are in millions, equals 643 e to the kt, using this equation right here. Please ask Mrs. Baker to pause this as is necessary so that you can get this down. Next step here, I divided both sides by 643. So this 1.409 represents 906 divided by 643. So I have 1.409 equals e to the 16k. Then to change this from exponent form to log form, it's natural log because it's base e. Natural log of 1.409 equals 16k. You're going to evaluate 1.409 in your calculator, divide it by 16 to equal k, and then that k is what goes up in the exponent here. I need a t as well. Okay, so then this represents the exponential growth model to which we can plug in any initial population in time to get a final population. So we're going to use that in part B to find in which year Africa's population will reach 2,000 million, which is 2 billion. So we put 2,000 million here as the final population. The initial population, again, A naught was 643, that goes here. E to the kt. So k is what I got from the part A. Then go ahead and divide both sides by 643 here. So this is 3.11 equals e to the 0.0214t. This is where we change to log form. My mouse. All right, then to log form is actually natural log of 3.11 equals the exponent here. Again, evaluate with the calculator, natural log of 3.11, divide that by 0.0214, and then you get t is approximately 56 years. So it says by which year, so I need to go ahead and add that 53 to the initial year, which was 1990. So the answer for this is year 2043. All right, switch to the next page or the back side. Take a couple minutes to read the paragraph here in example 2, and you can pause while you do that. Take a couple minutes to read the paragraph and the question, and pause while you do that. Okay, so here is the solution to number 2. Okay, so for part A, you want to start with the equation that we have from the front side. Remember that initial amount is A naught, final amount is A. So it says use the fact that 5715 years is the half-life, so carbon-14 will have decayed to half the original amount. So I use the original amount is 2 and the final amount is 1. You could use any two amounts here where the final amount is half of the original amount, because then in my first step I will divide both sides by 2 here. So whatever two amounts you use, as long as this is double the final, when you divide 1 divided by 2 like I did, you're going to get 0.5 here. So we have 1/2 equals e to the 5715k. This is where I change forms to log form. So this is natural log of 1/2 equals the exponent here. And then evaluate this in the calculator. Natural log of 1/2, close the parentheses, divided by the 5715. All right, go ahead and pause a second to make sure you can write this down and get that in the calculator. In part B, take a second to read that part. says analysis indicated that the scroll wrappings contained 76% of their original amount. So in this part, I've started with the original equation, although I've substituted in the K that we found in part A. Okay, so this is the model. The model means the equation that we found. Started up here with that. The original amount I'm going to let be 1, and then this is 76% of that, so 0.76. If the original amount is 100, then the final amount is 76. Okay, so now I divide both sides by 1, so that doesn't change anything here. Change forms, natural log of 0.76 equals the exponent. And then divide both sides by the 0.000121 to get t is approximately 2268 years. Okay, take a second to pause, make sure you write that down and you can do the calculations. Take a minute to read example 3 and go ahead and pause while you do that. Okay, in part A, it says how many people will become ill with the flu, or became ill with the flu when the epidemic began. So, if you look up here, it says who will have become ill with influenza T weeks after its initial outbreak. So when it began would be at time equals 0, 0 weeks after outbreak. So I took the formula here, wrote that down, and put in 0 for T. Remember, this brings us to e to the 0 power right here. 0 times 1.5 is 0, so e to the 0 power is 1. This gives me 30,000 over 1 plus 20. So 30,000 over 21 is approximately 1429. Take a second to pause, write that down, and make sure you can do the calculations. Part B. How many people were ill by the end of the 4th week? So that's T weeks after its initial outbreak, 4 weeks after, so T is 4 here. Again, using the original formula. And then if you use parentheses in the correct places, you can go ahead and type all of this into your calculator. Just make sure that you have everything in parentheses where it needs to be. So that should be approximately 28,583. Okay, take a second to pause to make sure you can put that in the calculator and get the correct answer. And then in part C, what is the limiting size of the function that becomes ill? Well, here it says the town has 30,000 inhabitants, so more than that cannot get sick. So this is the maximum number of people that can get the flu. The limiting size is 30,000. All right, that completes the notes. You have a worksheet 3.4 and 3.5 to work on today, and that is due tomorrow. Have a good day.